So good afternoon, class. As we had agreed, today we'll look at the indices, and we would want to mainly look at the rows of indices as we use them in the calculation or working out some problems. So we have already started the class. So hope we can hear each other, class. So as we had agreed, today we are looking at indices, and more so would want to look at the laws that we normally use, and these ones are also helpful when it comes to solving problems in logarithms. So with me, I'll share one of the documents that I had sent last week, and this is on the indices. All of us, I hope we have this document, which I had shared with you on your WhatsApp group. And would want to understand first, what is an index? In the Riemann language, this is what we normally call the power. And when it comes to evaluating problems involving different powers, we involve the various operations, say multiplication, division, subtraction, and so on. But more importantly, we would want to know when the base is the same. For example, if you have to look at the expression on the 3 times quite a number of the same element raised to a given power, how do we go about solving such problems? For example, if you are to look at what we have here, here we have 3. 3 is what we call the base. We can raise it to a given power or an index. For example, in this case, multiplying 3 4 times, then we can say the base is 3. How many times has that 3 been multiplied by itself? 4 times. So 4 becomes that particular power. And our base 3 here can actually be replaced by any other value. This is what we are calling the base. And this is what we call the power. Alternatively, we call it an index. Okay. So when we are looking at these variables, we would want to understand when an operation now is involved. Let's say we are multiplying, we are, for example, dividing, or we are maybe adding or subtracting. How do we deal with those powers? Okay. So let's look at some of the examples which are illustrated on that document. When we have a given value, let's say an element like 4 raised to the power of 2, when we are raising it to that particular power, we can either use a calculator to work with it. Alternatively, we can just work out manually. But when the numbers become tedious, let's say they are too big, we advise that we go for the use of the calculator. In high school, you are using logarithms, but this time we have the calculator to help us to work on these variables. Like when we say 4 is the power of 2. 2 is not a big variable. We can multiply 4 2 times by itself, and then we end up having a value, for example, 16. How about 5 raised to the power of 3? We multiply 5 3 times, and that one can do it even manually, although we say calculator would actually ease our work. Let's now introduce the laws themselves, and we are going to start with what we call the additional rule. This is the first law of indices, where given the same base, you can see the base is the same. What do we do with the indices, or what do we do with those powers? We normally sum the powers. Say a raised to the power of m multiplied by the same base a raised to the power of n. What we are going to have is to maintain the same base, and then we actually add the powers. For example, when we have the base of 7 raised to the power of, say, 6, multiplied by the same base raised to the power, let's say 4 here, what you're supposed to do is to just sum over the powers. But remember, before you sum over the powers, you must consider that those particular bases are the same. For example, here we could have had, let's say, 49. What are we supposed to do? Assuming this was, say, 49 times, let's say, 7 to the power of 4. What do we do in this case? We are going to change our 49 to constitute the base of 7, so that we are now able to add the powers. I can write 7 to the power of 2 to mean the same value of 49. And then we multiply this one by 7 to the power of 4. Because now we have the same base, we can maintain that base. And then what do we do with the powers? We are going to sum the powers. So here we'll have 2, we add it to 4. And we can't leave it like this. Remember, you have to maintain a simplified form of your work as much as possible. So lastly, we'll have 7 raised to the power of 6. And if you can use the calculator, you can now finally provide the answer to that particular problem. So that is one of the rules we use when it comes to dealing with variables which are involving powers, or whatever we are calling indices. Let's go to law number 2, and this is what we call the subtraction law. And subtraction law is dealt with when we are dividing. When we are dividing values which do have indices or powers, when that base is the same, the rule states we subtract the powers. And the rule is the numerator, its power, to subtract the power of whatever we have on the denominator. Always we start with the variable, or rather the power that is on the numerator variable, and then we minus the power of the value that is on the denominator. So again, before you subtract, ensure that the base is actually the same. So you look at, first of all, how can you simplify your work? Let's say these two bases were not the same, but can they share a particular value, and then you establish it in terms of an index? If so, you have been able to maintain the same base, then the rule is that you go ahead and you subtract the powers. A good example in our document here, we see we have 8 to the power of 5. We divide by 8 to the power of 3 because 8 is the same. This is our same base. We can go ahead and subtract the powers. But we are saying before you subtract, ensure that your base is actually the same. Similarly, when we have another value other than 8, it can be, for example, 120, it can be 2, it could be anything else. With a Z representing now any other value, what you're supposed to do here is to actually consider the same base, and then again we subtract those particular powers. So if our bases were not the same, what do we do? For example, let's assume we had a 3 to the power of, say, 9. And then we are dividing this one by, let's say, 27. So what do? We are going to express the 27 in form of a base that can be equivalent to the smallest possible value. In this case would be 3. So we can write this one as 3 to the power of 9. And then we divide this one by, say, 3 to the power of 3, which is the same as 27. Now, because we have the same base, we can go ahead and employ our rule, which states we have 3 as our base, and then we just subtract our powers. The value on the numerator to minus that power on our denominator value. And lastly, you can't leave your work like this. You end up having 3 to the simplified form to the power of 6. But finally, you can work on this using the calculator. The third law is where a particular value may have a power, and then again, the whole of that is raised to another power. And these powers can even be fraction, can be decimal numbers, or even negative kind of values. So what you're supposed to do is you just open up the bracket, just like in the normal way, where we say 2 into bracket 3 would actually be 2 times 3. So you just open up the powers themselves and not the base. So you maintain the base, but when it comes to now combining these powers, remember you are multiplying those powers. A good example, we have here 6, which is raised to the power of 4, and again raised to the power of 2. So what do? We open up by multiplying the powers first, which would be 4 times 2 to give us 8, but we still retain the same base. If it is any other value, our small letter e here is representing any other value. Can be, let's say, 0.1, can be 5, can be fraction value. Any other, the same rule would actually apply, that you just open up the powers by multiplying the corresponding powers. Let's do another maybe example of the same kind, and we see also how we can open up the powers. Let's say we have 3 raised to the power of 6, and then again all these we are supposed to raise the power of, let's say, 3. So what do? We maintain our base, but now we multiply our corresponding powers. And then finally, you can see we can raise 3 to the power of 18, which means you had raised it to the power of 6, and then the result you raise it to the power of 3. But in a simpler way, you just raise it to the power of 18, where we had already opened up our bracket here by multiplying the corresponding powers. Our last element that we'd want to demonstrate is actually a number in mathematics, which is raised to the power of 0. And this one, it's important we note, it will always give us a a number of 1. Any number raised to the power of 0 would always be equivalent to 1. From the logarithm, we normally say a variable to the base of itself will always be equivalent to 1. And that one is actually the index to which the number has actually been raised to. So again, lastly, our additional rule, which we borrow from logarithms, is that a raised to the power of 1 or any other number will always be equivalent to that number. But when a number is raised to the power of 0, the result is always what? Is always equivalent to 1. Maybe I can talk about this. The logarithm of a number to the base of itself will always be equivalent to 1. Maybe we'll also take time. I take you through those rules that we normally use in logarithm, although you already have that particular document. So if we were to raise this number to the base itself here, if you are to raise it to the index, this is the value we normally call an index in logarithm language. If you are to raise our value a here to the index, the result would actually be the number a here. That is what we normally interpret when it comes to logarithms. So our exercise here, but as I say, when you have a number, when you have a number raised to a 0, the result would always be equivalent to what? To 1. Okay? Very important here to understand. So in logarithm, how would I write this? Maybe just to touch on this. The logarithm of 1 to the base of a. Log of 1 to the base of a is always 0. And you can even check this one from your log books. If you still have them, you'll actually understand the log of 1 is always 0. Because the log of 10 to the base of 10 is actually 1, although that 10 represents any other number to the base of itself. Our exercise here is actually incorporating quite a number of laws that we have talked about. The additional law, the subtraction, the combination, which we call the product rule, as well as the general cases of a logarithm of 1, and also the log of a number to the base of itself, which mathematically we say when a number is raised to the power of 0, the result is 1, and when a number is raised to 1, the result is that number. Our exercise here, let's try and do, for example, number A. We have 5 raised to the power of 3 multiplied by 5 to the power of 13. Because we already have the same base here, we are not going to change the base, and therefore we are going to have what? We are going to have 5 raised to the power of 3 And then that 3, we add it to a 13. So lastly, we end up having, for this example here, we'll have 5 raised to the power of 3. Adding, because we're talking of multiplication, we add it to the power of 13. And 3 and 13 will give us the index here indicated as 16, as you can see from our screen there. Okay. Assuming we have a number which is not known, like an x here, and we are still multiplying with different powers indicated here, what are we going to have? We'll still maintain the same base, don't change it to any other number, just use whatever is given, and then we end up adding our powers. So lastly, whichever the number we have, it doesn't matter. It can be a fractional, a decimal, or a negative value. But the point is, when you're multiplying, we are supposed to, you can see here the multiplication is our operation to consider. We are going to, again, add this particular powers. So 6 plus 5, which now gives us the x that you see here as our answer, which is actually raised to the power of 11. Okay. How about when we are combining the powers? We have said maintain the same index. For example, number D here, a to the power of 3 to the power of 4 again, we just multiply those indices. So 3 times 4, and that will definitely give us the same base a raised to the power of 12. Okay, let's do one on the division. I'll take number F here. For F, we have an x raised to the power of 8 divided by x to the power of 7. So because we are dividing, then it means the rule should be we subtract the powers. And then we end up having an x, 8 minus 7 is 1, which, if you are to remember our last statement, we have said a number raised to the power of 1 will always be that number. Going back to what we have here, you'll understand why we call it now x. Again, when it comes to division, you can now try number E here. You just subtract the powers because the base is actually the same. Sometimes you're given some complex numbers, and what you're supposed to do is to actually leave your work in a very simplified form. As much as possible, try to simplify your work. So when you are dealing with values which are very large, try and look for a very simple base that you can deal with before you combine your different variables given. Now, I would like to give a small exercise which I want you to try during your free time.
Brenda, return.
Trying to combine the various rules that we have talked about. So maybe you can write down this particular.
When you get in a bedroom,
you can try to do this exercise. Kindly mute yourself, those who are joining in, that you can have one meeting. Okay, this is our today's exercise, which I want you to try as we employ those rules we have talked about. So I'm going to give it on this platform. Question number 1, our homework for today. Remember, in all my classes, you must take home some work. And since you're at home, you just try this one immediately. Question number 1, you are going to work out the following. You have 8 raised to the power of 1 equivalent to 2 m raised to the power of 2. So what I want you to do is to find what is m in this particular exercise. And before you work on m, try and maintain the same base. Like you can simplify 8 in terms of 2, so that by the end of the day, you can now equate the powers, and now you work on the unknown. So I've given you a hint on what to do on that exercise. Number 2, you are going to simplify the following. We have 7 raised to the power of 18 raised to the power of 18. We divide this one by, we are dividing 7 raised to the power of 3, and then the whole of this is again raised to the power of 2. Remember what to do as you open up the bracket when you have got say more than one power involved. Then work out on the following. Raise the power of -2 times 64 raised to the power of 1/2. Question number 4. We have 25 raised to the power of 4 equivalent to 5 raised to the power of 8. Again, you make sure you have simplified the workings to have the same base. So here, I want you to look for what is x in that example. And lastly, you are going to write the following expression. You write the expression 27 to the power of minus a third as a fraction. So hope that is not too much to ask for today's class. So let me make this one better. This was to the power of 18. Remember, you're dividing there. So you do that exercise. If there'll be any challenge you'll face along the way, you may raise it on your WhatsApp group. I'll be able to respond on that. So we mark the end of our today's session, hoping that we can have more of this so that we'll be able to help each other to iron out the issues which could be pending. You can also suggest on what could be bothering you on the same platform. I'll be able to pick it up, and in the next class, maybe we can set some few minutes to actually look at such a problem, which could be a big issue from your end. I also believe that we are revising because at the end of the day, whichever the date will be set, one day, one time, we'll have to do the exam. We may not be able to say exact date is this because of the situation currently, but at the end of the day, we'll have to do the exam. So we stop there for today. I've made a record on our today's class. I will share it later on the same platform. So I unmute you. You may ask a question if you have any. Is there anyone with an issue that could be burning that we can look at it next time?
Yes.
Yes,
What is the problem?
logarithm.
Logarithms. So
Yes.
can we set that to be our next meeting? Next week, Monday, is it okay? The same time?
And
Yeah.
the card you gave us,
The cat.
we face some challenges we need to correct. Yes.
What was the problem?
There was a problem in calculating the mode.
Mm-hmm.
Yes.
Okay, we'll look at that, yeah? But
And
Okay.
also,
can we say that in our next class, we now look at the logarithms?
yes.
Okay, for the indices, you have understood the class for today?
Yeah.
Okay, follow up that document as many times as possible. And then if you can take it aside as you do this exercise, I think it can be very helpful. If you still have a challenge, you let me know. Okay.
Yes.
Okay.
Okay, I end the meeting now. Thank you for your attendance. And you share this with the rest. I see our attendance is very low. Kindly share this with your friends.
Okay.
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 Yes.